racing through the silent darkness between stars at 58 kilometers per second. Something ancient has recently entered our cosmic neighborhood, something that should not exist. 3I-ATLAS. A wanderer older than our entire solar system, carrying chemical fingerprints from when our galaxy was young and metal poor, when conditions for planetary formation were supposedly impossible. Yet here it blazes through our telescopes, outgassing water vapor that has been frozen for 11 billion years. We have always believed we understood planetary formation. The first rocky worlds, the first icy comets, the first building blocks of life emerging only after generations of stars had enriched the galaxy with heavy elements. But what if we were wrong? What if massive, water-rich worlds were forming in the ancient galaxy billions of years before our solar system even existed? Tonight, on the Sleepy Explorer, we follow this messenger from the galactic dawn as it makes its closest approach to our Sun, carrying within its pristine nucleus the direct evidence of planetary processes from an epoch we can barely comprehend. We will trace its billion-year journey across space and time, examine the controversy surrounding its statistically impossible trajectory, and investigate why this ancient comet challenges fundamental assumptions about when and where life's building blocks could form. Prepare yourselves. We begin. It's difficult for us humans to fully comprehend the enormity of space. We are comfortable in our own cosmic neighborhood, the solar system, and are used to familiar faces like Jupiter, Mars, and of course, Earth. But out there, over 18 billion kilometers away from the Sun and beyond the heliopause, lies the cold oblivion of interstellar space. In the vast silent expanse of the Milky Way, our solar system is not an island. It is a traveller on a galactic current, periodically crossing paths with messengers from other stellar shores. For millennia, these encounters went unnoticed, lost in the infinite darkness between stars. The two Voyager probes are the only human-made objects ever to cross the threshold into this cosmic wilderness, carrying our first tentative messages to whatever might be listening in the void. Until recently, only two known objects had ever made the opposite journey, passing from interstellar space into our solar system. These were the famous 1I, Oumuamua in 2017, and 2I, Borisov in 2019, which brought with them the thrill, and perhaps even fear, of being visited by something from the depths of space that humans cannot hope to reach in our lifetimes. Each was a profound discovery, a single data point hinting at the nature of planetary systems beyond our own, visitors from stellar neighborhoods we can barely imagine. Oumuamua arrived like a ghost, tumbling through our solar system with its strange elongated shape and mysterious acceleration, departing almost as quickly as it came. It left behind more questions than answers, a cosmic riddle wrapped in an enigma. Borisov followed 2 years later, more familiar in its cometary behavior, yet still alien in its composition, carrying chemical signatures of a stellar system fundamentally different from our own. In the 6 years since these visits, we had been enjoying some respite from the cosmic unknown. Astronomers continued their patient vigil, scanning the skies with ever more sophisticated instruments, knowing that eventually another messenger would arrive from the galactic depths. But when it came, it would eclipse its predecessors in nearly every respect, heralding a new era in the study of extrasolar planetesimals. On the 1st of July, 2025, that moment arrived. A recent observation forced the astronomical community to sit up and pay attention once more, as telescopes detected something extraordinary racing toward our Sun from the direction of the constellation Sagittarius. This third confirmed interstellar object would prove to be not merely another cosmic rock, but a pristine, tangible sample from a planetary system that likely formed billions of years before our own, a relic from the galactic dawn. Designated 3I-ATLAS, This visitor carries within its ancient nucleus the chemical fingerprints of a time when our galaxy was young, when the first generations of planets were forming around metal-poor stars in the thick disk of the Milky Way. Its immense size, unprecedented speed, and peculiar trajectory have provided an unparalleled opportunity for scientific study, mobilizing the world's most powerful observatories in a coordinated campaign of observation and analysis. Yet the very characteristics that make 3I-ATLAS a scientific treasure have also ignited a firestorm of public fascination and controversy. Its statistically improbable orbit and initial ambiguity have fueled speculation that it might be more than a simple comet, with some prominent voices proposing it could be an artifact of extraterrestrial intelligence, a probe from a distant civilization conducting reconnaissance of our solar system. The data returned from this cosmic visitor has been nothing short of revolutionary, offering the first direct glimpse into the chemical composition and physical nature of a body forged in the ancient, metal-poor environment of the galaxy's thick disk. Every photon of light captured from its surface, every spectral line analyzed, every measurement of its trajectory tells a story that stretches back through billions of years of galactic history. This is the story of 3I-ATLAS, how it was discovered, what it has revealed about the ancient galaxy, and how it has served as both a window into the formation of distant worlds and a powerful test of our scientific methods. It is a tale of international cooperation, technological triumph, and the eternal human drive to understand our place in the cosmos. Most importantly, it demonstrates how this single object has revealed a field of study that has rapidly come of age, transforming from serendipitous discovery to systematic science. The journey of 3I-ATLAS began billions of years ago in a stellar system we will never see, around a star that may no longer exist. But its story in our solar system began on a quiet July evening in the Atacama Desert of Chile, when a robotic telescope captured 4 images that would change our understanding of the galaxy forever. 2. The Hunt, Modern Sky Surveys and the Art of Discovery, 1,200 words, the story of 3I-ATLAS, is a testament to the power and efficiency of modern automated sky surveys. Its detection and subsequent confirmation unfolded with a speed and precision that would have been unimaginable just a decade prior, showcasing a global astronomical community now primed and ready for the arrival of visitors from beyond the void. At the heart of this detection capability lies the Asteroid Terrestrial Impact Last Alert System, ATLAS. This NASA-funded network consists of 4 telescopes strategically positioned across Chile, South Africa, and Hawaii, each scanning the heavens with mechanical precision. Night after night, these robotic sentinels capture around 800 images each, their combined efforts having registered 212 near-Earth objects that will pass within 1.3 astronomical units of our planet at perihelion. It is a remarkable achievement in planetary defense, a global early warning system for cosmic threats. But ATLAS possesses a unique capability that sets it apart from other sky surveys. While projects like Pan-STARRS and the Catalina Sky Survey are often too sensitive to photograph the bright, disc-shaped region of our galaxy, the galactic plane, where most of its mass lies without facing overexposure, ATLAS can peer directly into this cosmic maelstrom. This ability would prove crucial on the night of the 1st of July, 2025. The ATLAS telescope at El Source Observatory in Rio Hurtado, Chile, was performing its usual systematic sweep of the sky. Observatory code W68 methodically captured 4 30-second survey images pointing toward the constellation Sagittarius, that dense stellar region harboring our galaxy's central supermassive black hole. Hidden among the countless stars was an object making a beeline toward our solar system, traveling at a velocity that defied comprehension. Initially designated with the prosaic name A11PL3Z, this faint speck of light quickly caught the attention of the Minor Planet Center, MPC, in Cambridge, Massachusetts. As the designated global authority for labeling and tracking minor bodies in the solar system, the MPC serves as mission control for cosmic discoveries. When the alert reached their computers, astronomers realized they were witnessing something extraordinary. The object's motion was so unusual that suspicions were instantly raised about its origin. Its trajectory was unlike anything native to our solar system, moving with a speed and direction that spoke of origins in the depths of interstellar space. Within hours, the MPC had issued an electronic circular detailing all previous observations and providing crucial information about the object's trajectory. But, as astronomers dove deeper into archived data, they made a remarkable discovery. This cosmic visitor was no stranger to their instruments. The Zwicky Transient Facility in California, along with the 3 other ATLAS telescopes, had all made precovery observations of the object dating back to the 14th of June. Like archaeologists uncovering layers of history, scientists mined through weeks of stored images, each observation helping to refine their understanding of the visitor's path. The most significant precovery came from an unexpected source. NASA's Transiting Exoplanet Survey satellite, TESS, designed to hunt for planets around distant stars, had serendipitously observed the object nearly continuously between May 7 and the 3rd of June, 2025. These space-based observations provided the earliest known photometric data, extending the observational baseline and allowing astronomers to trace the object's journey back through months of interstellar approach. Perhaps most prophetically, the newly commissioned Vera C. Rubin Observatory in Chile had also captured images of 3I-ATLAS during its science validation phase, starting on the 21st of June, 2025, a full 10 days before the official ATLAS discovery. This wasn't merely a footnote in astronomical history, but a powerful preview of the future. Had the Rubin Observatory's validation program begun just 2 weeks earlier, it would have claimed the discovery for itself, heralding a new age in cosmic archaeology. With all this data combined, the MPC's analysis revealed an orbit with exceptionally high eccentricity, approximately 6.14. This number was the smoking gun that definitively proved the object had originated from interstellar space, far beyond the gravitational influence of our Sunday. On the 2nd of July, 2025, the MPC issued Minor Planet Electronic Circular MPEC 2025N12, formally announcing that the object was of interstellar origin and bestowing upon it the official designation 3I-ATLAS. But there was more. Early observations revealed something that transformed the discovery from remarkable to revolutionary. Multiple observatories, including the Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada, France, Hawaii Telescope at Mauna Kea, reported tentative signs of cometary activity. They described a marginal coma, a diffuse halo of dust and gas, and a short, 3-arcsecond tail-like feature extending from the object. The implications were profound. This wasn't just another interstellar asteroid like Oumuamua. This was a comet, actively sublimating its ancient ices as it approached our Sun, releasing material that had been locked away since the formation of a distant planetary system billions of years ago. The object's dual nature was reflected in its multiple designations: 3I-ATLAS for its interstellar origin, and C 2025 N1 ATLAS for its cometary classification. The rapid confirmation process marked a profound shift in the study of interstellar objects. The discovery of Oumuamua in 2017 had been largely reactive. The object was already past its closest approach to the Sun and heading back to interstellar space when scientists fully realized what they were observing. In contrast, 3I-ATLAS was identified far out on its inbound trajectory, providing months of lead time for a coordinated, global characterization campaign. This new paradigm is epitomized by what lay ahead. While current surveys had managed to find 3 interstellar objects in 8 years, the Vera C. Rubin Observatory, with its vast field of view and unprecedented sensitivity, is projected to discover dozens, perhaps even hundreds, of such objects over its initial decade of operations. This will transform the study of interstellar objects from the analysis of individual curiosities into a true statistical science, where fundamental questions evolve from what is this specific object to what are the bulk properties, demographics, and distribution of planetary building blocks across the galaxy. 3I-ATLAS, discovered on the very cusp of this new era, serves as both a spectacular final catch for the current generation of surveys and the inaugural test case for the next. Its story demonstrates how modern astronomy has evolved from chance encounters to systematic discovery, from individual observations to global coordination, from reactive science to proactive cosmic archaeology. 3. Reading the Cosmic Passport, Orbital Mechanics as Detective Work, 1,500 words. The orbit of 3I-ATLAS serves as its cosmic passport, encoding the story of its extraordinary journey across the galaxy. Every parameter of its trajectory distinguishes it from any known object native to our solar system and even from its interstellar predecessors, telling a tale of extreme energy and peculiar geometry that has become the source of both intense scientific interest and speculative controversy. To understand what makes this orbit so remarkable, we must first grasp the mathematics of celestial mechanics. The fundamental proof of an object's interstellar nature lies in the shape of its orbit, mathematically described by its eccentricity. This single number tells us everything about an object's relationship with our Sun and its ultimate fate. An object in a perfectly circular orbit has an eccentricity of 0. Think of the nearly circular paths of Venus or Neptune. Objects in elliptical orbits, like planets and most comets, have eccentricities between 0 and 1, with higher numbers indicating more stretched, oval-shaped paths. An object with an eccentricity of exactly 1 follows a parabolic escape trajectory, possessing the minimum energy needed to leave the solar system and never return. But any object with an eccentricity greater than 1 follows a hyperbolic path, the mathematical signature of a visitor from interstellar space. Such objects arrive with excess kinetic energy that our Sun's gravity cannot overcome, marking them as cosmic wanderers that will eventually return to the void between stars. 3I. Atlas possesses the most extreme hyperbolic orbit yet measured, with an eccentricity of approximately 6.14. This staggering value dramatically exceeds those of its interstellar predecessors, Oumuamua's modest 1.2 and Borisov's more substantial 3.6. The number represents a fundamental truth about this cosmic visitor. It is far more gravitationally unbound to our Sun than even its fellow travelers from distant stars. This extreme eccentricity translates into breathtaking speed. To visualize the velocity of 3I-ATLAS, imagine running the length of 580 football pitches every second. That's its hyperbolic excess velocity of 58 kilometers per second relative to the Sunday. At the time of its discovery near Jupiter's orbit, it was already racing through space at 61 km per second, with calculations showing it will peak at a blistering 68.3 km per second as it reaches its closest point to the Sunday. This immense speed dwarfs its predecessors, Oumuamua's 26 km per second and Borisov's 32 km per second seem pedestrian by comparison. Such velocity cannot be achieved by any object originating in our solar system. even with gravitational assists from all the giant planets. It is the indelible signature of a body that has journeyed across the galaxy, propelled by the ancient dynamics of its birth system and shaped by billions of years of interstellar wandering. But speed alone doesn't tell the full story. The most scientifically puzzling and controversial aspect of 3I-ATLAS's trajectory lies in its geometry. The object's orbital inclination measures 175.11 degrees, a number that has sparked intense debate about the nature of this cosmic visitor. To understand why this number is so significant, consider that an inclination of 180 degrees would represent a perfectly retrograde orbit exactly within the ecliptic plane, the flat disk in which all of our solar system's planets orbit the Sunday. 3I-ATLAS is travelling in the opposite direction to the planets, but its path is tilted by only about 5 degrees relative to their orbital plane. It's as if this interstellar visitor chose the most convenient highway through our planetary neighbourhood. The probability of a random object arriving from interstellar space with a trajectory that aligns so closely with our solar system's fundamental plane is extraordinarily low, calculated at a mere 0.2%. This single statistical improbability has become a focal point of scientific debate, giving rise to two fundamentally different interpretations of the same data. From the mainstream scientific perspective, this alignment represents a fascinating puzzle worthy of investigation. While improbable, such low probability events are expected to occur, eventually given the sheer number of stars and ejected planetesimals in our galaxy. The alignment could provide crucial clues about the object's origin, perhaps indicating that planetesimals are preferentially scattered from their home systems along the galactic plane, or it might point to selection biases in our detection surveys, which are optimized to find objects near the ecliptic. From a more speculative viewpoint, championed by Harvard astronomer Avi Loeb and his collaborators, the low probability suggests not chance but intent. In this interpretation, the orbit appears fine-tuned to allow for an efficient survey of the inner planets of our solar system, precisely the trajectory an intelligent probe might choose for reconnaissance of our cosmic neighbourhood. The object's path takes it on a grand tour of the inner solar system, arriving from the direction of Sagittarius and following an asymptotic approach that will bring it to perihelion, its closest approach to the Sun, on the 30th of October 2025. At that moment, it will be at a distance of approximately 1.4 astronomical units, placing it just inside the orbit of Mars and following a trajectory more similar to Borisov's path than Oumuamua's much closer solar encounter. For those concerned about potential threats to Earth, the object's trajectory provides complete reassurance. Its closest approach to our planet will be a very safe 1.6 astronomical units, more than 240 million kilometers away, or roughly 600 times farther than the distance to the Moon. We can observe this cosmic visitor from the comfortable safety of our terrestrial vantage point. A direct consequence of 3I-ATLAS's near-ecliptic path is a series of relatively close planetary encounters. The minimum orbit intersection distance calculations reveal remarkably small separation values. Mars at 0.0179 AU, Jupiter at 0.2467 AU, and Venus at 0.65 AU. These close passes aren't independent coincidences, but geometric consequences of the object's alignment with our planetary system's fundamental plane. This trajectory dictates the observational campaign timeline. The comet remains visible to ground-based telescopes through September 2025, offering months of detailed study as it approaches the Sunday. As it nears perihelion in late October, it will pass into solar conjunction, disappearing behind the Sun's glare as seen from Earth. This period of invisibility has become a key point of discussion, particularly among proponents of artificial origin theories. who suggest it provides the perfect opportunity for a clandestine reverse solar Obert maneuver, a hypothetical spacecraft braking burn to enter a bound solar orbit, while hidden from Earth's view. However, this speculation presents a uniquely testable prediction. Such a maneuver would cause a significant, easily detectable change in the object's trajectory. While Earth-based observatories will be temporarily blinded, several interplanetary spacecraft, including ESA's Jupiter, Icy Moons Explorer, JUICE, and various assets at Mars, will maintain clear sightlines to 3I-ATLAS during its solar passage. These robotic observers can precisely track its motion, providing independent verification of its path. When 3I-ATLAS re-emerges from behind the Sun in early December 2025, ready for another round of observations, its trajectory can be precisely measured and compared to predictions. If it remains on its calculated hyperbolic path, with no deviation beyond natural cometary outgassing effects, it will serve as powerful evidence against artificial intervention theories. The December observations will mark a crucial moment of scientific verification, where theoretical predictions meet observational reality. The orbital characteristics of 3I-ATLAS represent far more than mere astronomical curiosities. They encode the history of its billion-year journey, the dynamics of its ancient birth system, and the fundamental physics governing objects that traverse interstellar space. Whether viewed as a natural wonder or potential artificial construct, its trajectory serves as a cosmic Rosetta Stone, waiting for us to fully decipher its ancient message about the nature and distribution of planetary building blocks throughout our galaxy. 4. Portrait of an Ancient Wanderer. Physical characterization. 1. 800 words. The extended inbound observation window for 3I-ATLAS has provided astronomers with an unprecedented opportunity to conduct an intensive, multi-wavelength characterization campaign. What emerged from months of careful observation is a detailed physical portrait of an object that is both broadly familiar in its cometary nature and uniquely extreme in its properties, a cosmic time capsule that has preserved the detailed conditions of planetary formation from the ancient galaxy. From the moment of its discovery, 3I-ATLAS announced itself as something special through its remarkable brightness. Unlike the faint, fleeting glimpse we had of Oumuamua, this interstellar visitor blazed across our detectors with an intensity that immediately caught astronomers' attention. The comet had remained relatively faint through most of its approach, maintaining a magnitude of around 20 until late May 2025. But between then and its July discovery by ATLAS, something extraordinary occurred, a dramatic brightening that saw its magnitude surge to between 17.7 and 17.8 inch, the ATLAS O-band, which records light wavelengths between 560 and 820 nanometers. This brightness surge wasn't merely a testament to the comet's approach, it was evidence of awakening. As 3I-ATLAS drew closer to our Sun, solar radiation began to penetrate its ancient surface, sublimating ices that had remained frozen for billions of years. The resulting cloud of gas and dust created a glowing halo that scattered sunlight, transforming a dark, distant speck into one of the brightest interstellar objects ever detected. Initial estimates based on this brightness, assuming typical cometary reflectivity values, suggested a nucleus diameter that defied belief, potentially 15 to 20 kilometers across. Such dimensions would make 3I-ATLAS not just the largest interstellar object ever detected, but potentially larger than many of the most famous comets in our own solar system. However, these early estimates faced a fundamental challenge. They couldn't distinguish between light reflected from the nucleus itself and light scattered by the surrounding coma. The first major refinement came from analysis of precovery images captured by the Vera C. Rubin Observatory during its science validation phase. By carefully separating the compact central nucleus from the diffuse surrounding coma, astronomers revised their estimates downward to approximately 11.2 kilometers, still enormous by interstellar object standards, but more in line with theoretical expectations for large cometary nuclei. The most definitive measurement arrived courtesy of the Hubble Space Telescope. On the 21st of July, 2025, Hubble's advanced cameras captured the sharpest images yet obtained of the comet, allowing astronomers to place firm constraints on the nucleus size. This analysis established an upper limit of 5.6 kilometers for the nucleus diameter, with possible lower bounds as small as 320 meters. While smaller than initial estimates suggested, this still comfortably establishes 3I-ATLAS as the largest interstellar object ever detected, dwarfing Oumuamua's estimated 400-meter length and Borisov's sub-kilometer dimensions by a significant margin. But 3I-ATLAS distinguished itself through more than mere size. Within days of its discovery, the debate over whether this visitor was an asteroid or comet was definitively settled. While initial observations showed only a point source of light, follow-up imaging quickly revealed the telltale signs of cometary activity, a diffuse fuzz surrounding the central nucleus that marked the presence of a coma. This cometary classification received its most compelling confirmation from NASA's Neil Gehrels Swift Observatory. Between the 31st of July and the 1st of August 2025, Swift's ultraviolet optical telescope made the first direct detection of water activity from the comet by observing ultraviolet emission from hydroxyl radicals, OH, molecules that form when water vapor is broken apart by solar radiation. This detection provided the smoking gun evidence that 3I-ATLAS is indeed a water ice-driven comet, operating according to the same fundamental processes that govern comets from our own solar system. However, the activity of 3I-ATLAS proved unusual in its intensity and character. The measured water production rate of approximately 135 times 10 to the power of 27 molecules per second, roughly 40 kilograms per second, at a heliocentric distance of 3.51 AU, represents remarkably high outgassing for a comet so far. From the Sunday. At such distances, water ice sublimation is typically inefficient, suggesting either that an unusually large fraction of the nucleus surface is active, over 20%, compared to just a few percent for typical solar system comets, or that large icy grains ejected into the coma continue sublimating in space, acting as an extended source of water vapor. The comet's rotation provided another piece of the characterization puzzle. Through time series photometry repeatedly measuring the object's brightness over several nights, astronomers detected periodic variations caused by the nucleus's spin and irregular shape. Initial observations using Las Cumbres Observatory's 0.36-meter telescopes in Hawaii suggested a rotation period of approximately 29 hours, with surprisingly little brightness variation throughout each rotation cycle, only about 0.2 magnitudes compared to the dramatic fluctuations observed in Oumuamua. This minimal variability initially puzzled astronomers. Objects with highly irregular shapes typically show significant brightness changes as different surface areas and orientations face Earth during each rotation. The relatively flat light curve suggested either a more spherical nucleus than expected, or a more complex activity pattern that masked shape-related variations. Subsequent observations refined this measurement, with collaborative studies using multiple ground-based telescopes deriving a more precise synodic rotation period of 16, 6 plus minus 0.0, 1 hours, still unusually stable, but faster than initially calculated. High-resolution imaging from Hubble revealed yet another distinctive characteristic of 3I-ATLAS. Instead of the classic tail pointing directly away from the Sun that we expect from most comets, this interstellar visitor exhibits what astronomers describe as a teardrop-shaped cocoon of dust, or a prominent plume of material extending toward the Sun, a seemingly counterintuitive orientation that initially raised eyebrows among researchers. This unusual dust distribution, while uncommon, represents a known cometary phenomenon best explained by anisotropic outgassing. When material is ejected primarily from a localized hotspot on the Sun-facing side of a slowly rotating nucleus, the momentum of the ejected dust and gas carries it forward in the comet's direction of motion before solar radiation pressure can push it back into a traditional tail. Rather than indicating anything artificial about the object, this feature provides insights into the comet's surface properties and internal structure. As observations continued, the tail became better defined and more extensive. Initial reports described a modest 3 arcsecond feature at an angle of approximately 280 degrees, but contributions from amateur astronomers around the world coordinating through platforms like the Astronomer Telegram helped refine these measurements. Miguel Alarcón and colleagues reported that the tail extends across more than 25,000 kilometers of space, creating a spectacular sight for those with access to sufficiently powerful telescopes. The global amateur astronomy community's involvement in characterizing 3I-ATLAS represents a remarkable democratization of cosmic discovery. Daily updates on the Astronomer Telegram forum showcase contributions from observers worldwide, each adding pieces to the growing portrait of this ancient wanderer. Their high-quality images reveal not just the scientific value of citizen science, but the profound human connection to cosmic exploration that transcends national boundaries and professional affiliations. Spectroscopic analysis provided the deepest insights into 3I-ATLAS's composition and origins. Observations from major facilities, including the Gemini North Telescope, the Very Large Telescope, and the Southern Astrophysical Research Telescope, all consistently revealed that light reflected from the coma is moderately redder than our Sun, but similar to D-type asteroids found in the outer regions of our solar system's asteroid belt. D-type asteroids represent some of the most primitive bodies in our solar system, characterized by dark, reddish surfaces rich in complex organic compounds. The spectral similarity suggests that 3I-ATLAS formed from similar primordial materials, but in a stellar system with fundamentally different chemical conditions than our own. Near-infrared spectroscopy conducted with instruments like SPECS on NASA's Infrared Telescope facility provided even more detailed chemical fingerprints. While early observations didn't detect strong water ice absorption features on the nucleus surface itself, they found spectral evidence for approximately 10 micron-sized water ice grains within the coma. Detailed modeling suggests the coma represents an aerial mixture of roughly 30% water ice and 70% rocky, refractory material, with the rocky component best matched by primitive carbonaceous meteorites like the Tagish Lake specimen, one of the most chemically primitive materials known from our solar system. Notably absent from early spectroscopic observations were the emission lines of canonical cometary gases like cyanide, Cn, triatomic carbon, C3, or diatomic carbon, C2. This initially raised questions about the comet's composition and activity mechanisms, but subsequent analysis showed this absence to be entirely consistent with a water-dominated comet at large heliocentric distances. At the cold temperatures prevailing beyond 3 AU from the Sun, the sublimation of highly volatile ices that often drive early cometary activity simply hadn't begun in earnest. The later, definitive detection of OH emission by the Swift Observatory at a closer distance strongly validated the model of a comet whose activity is primarily driven by water-ice sublimation the most abundant and stable of the common cometry, ICES. As 3I-ATLAS continues its approach toward perihelion, astronomers expect to detect additional volatile species as rising temperatures unlock progressively more exotic ices frozen within its ancient nucleus. This comprehensive physical characterization reveals 3I-ATLAS to be a remarkably preserved sample of planetary building materials from the early galaxy. Its combination of large size, high activity levels, primitive composition, and ancient origins makes it an unparalleled laboratory for understanding how planetary systems formed under conditions vastly different from those that created our own solar system. Every measurement, from its rotation period to its chemical composition, adds another piece to the cosmic puzzle of planetary formation across space and time. Time Machine, Tracing Origins Through Galactic History, 1,500 words. Perhaps the most profound revelations about 3I-ATLAS have emerged from tracing its trajectory not just through our solar system, but backward through billions of years of galactic history. This kinematic archaeology has allowed astronomers to paint a portrait of the comet's likely birthplace and age, revealing it to be a true primordial relic from an epoch when our galaxy was fundamentally different from the stellar neighborhood we know today. The key to unlocking any interstellar object's origin lies in its velocity relative to the local stellar population. When astronomers subtract our Sun's orbital motion around the galactic center from 3I-ATLAS's observed velocity vector, they can determine how this ancient wanderer moves through what's called the local standard of rest, essentially the average motion of nearby stars in our galactic neighborhood. The result is startling. 3I-ATLAS possesses a hyperbolic excess velocity of approximately 58 kilometers per second relative to our Sun, a speed that immediately places it in a special category of cosmic travelers. This isn't just fast by solar system standards, it's fast by galactic standards, encoding a story of origin that stretches back to the dawn of planetary formation in our galaxy. To understand what this velocity tells us, we must consider how stellar populations in the Milky Way are organized and how they evolve over cosmic time. Our galaxy isn't a uniform distribution of stars, but rather a complex, layered structure with distinct populations that formed at different epochs and under different conditions. The thin disk of the Milky Way, where our Sun resides, contains the galaxy's youngest and most metal-rich stars. These stellar systems, born from gas clouds enriched by generations of stellar nucleosynthesis, orbit the galactic center in relatively circular, well-ordered paths with modest random velocities. Their orderly motion reflects their youth. They haven't had time to be significantly perturbed by gravitational encounters with giant molecular clouds, spiral arms, and other galactic structures. Surrounding this thin disk is the thick disk, a more diffuse and vertically extended population of older stars with distinctly different properties. Thick disk stars formed billions of years earlier from gas that was much poorer in heavy elements, the metals that astronomers define as anything heavier than hydrogen and helium. More importantly, for understanding 3I-ATLAS, thick disk stars have undergone billions of years of gravitational interactions that have heated their orbits, giving them higher random velocities and more extended paths around the galactic center. The velocity of 3I-ATLAS, 58 km per second relative to the local standard of rest, is too high to be typical of a thin disk system like our own. Instead, its kinematics strongly match those expected for objects ejected from thick disk stellar systems. This isn't merely a statistical correlation, it's a fundamental clue to the comet's age and the conditions under which it formed. Based on well-established relationships between stellar age and velocity dispersion in galactic populations, multiple independent studies have converged on a remarkable kinematic age for 3I-ATLAS, approximately 7 to 11 billion years old. To put this in perspective, our entire solar system is only 4.6 billion years old. 3I-ATLAS was already ancient when our sun first began to shine, a wanderer that had been drifting through interstellar space for billions of years before Earth even existed. This extraordinary age makes 3I-ATLAS not just older than its interstellar predecessors, it's roughly 30 times older than Oumuamua and 3 times older than Borisov, but fundamentally different in its cosmic context. While Borisov likely formed in a stellar system somewhat similar to our own, 3I-ATLAS represents a messenger from the galaxy's adolescence, a time when conditions for planet formation were radically different from what we observe today. The implications of this ancient, thick disk origin extend far beyond mere age determination. Stars in the thick disk are characteristically metal-poor, containing significantly lower abundances of elements heavier than hydrogen and helium compared to stars like our Sunday. This chemical signature reflects the evolutionary state of the galaxy when these systems formed a time before generations of massive stars had lived, died, and enriched the interstellar medium with the products of nuclear fusion. The detection and detailed characterization of 3I-ATLAS therefore provides the first direct, tangible evidence that large planetesimals could form efficiently even in the metal-poor environment of the early galaxy. This observation has profound implications for our understanding of planetary system formation and the potential for life throughout cosmic history. Previous studies of exoplanets around low metallicity stars had suggested that planet formation might be less efficient in metal-poor environments, since heavy elements provide the raw materials for building rocky planets and the solid cores of gas giants. The existence of 3I-ATLAS, a substantial, water-rich comet that formed in such an environment, challenges these assumptions and suggests that the building blocks of planetary systems were being assembled effectively even in the galaxy's youth. Moreover, there's a tantalizing connection between the comet's inferred origin and its observed composition. The detection of significant water activity in its coma, combined with spectroscopic evidence for primitive, organic-rich D-type material, aligns remarkably well with theoretical predictions for planetesimal formation in metal-poor protoplanetary disks. Some models suggest that lower metallicity environments might actually favor the formation of large, water-rich bodies like 3I-ATLAS, as reduced dust opacity allows solid materials to condense more efficiently in the outer regions of protoplanetary disks. The survival story encoded in 3I-ATLAS's journey is equally remarkable. For 7 to 11 billion years, this ancient comet has wandered through the harsh environment of interstellar space, subjected to cosmic ray bombardment, temperature extremes, and the gravitational perturbations of countless stellar encounters. Yet it has preserved within its nucleus the chemical fingerprints of its birth environment, maintaining its structural integrity across cosmic epochs that dwarf human comprehension. This preservation speaks to the remarkable stability of large icy bodies in the interstellar medium. Despite the hostile environment, 3I-ATLAS has retained enough volatile material to become highly active as it approaches our Sun, suggesting that substantial amounts of its original inventory of water, ice, and organic compounds have survived the billion-year journey. This discovery has profound implications for astrobiology and the distribution of life's building blocks throughout the galaxy. The chemical composition revealed through spectroscopic analysis, water ice combined with primitive, organic-rich rocky material represents a direct probe of conditions for life in the ancient galaxy. The fact that such materials were being assembled into large, potentially planet-building objects billions of years before Earth existed pushes back the timeline for when and where life might have first emerged in the Milky Way. Current estimates of interstellar object density based on ATLAS survey data suggest approximately 0.001 objects per cubic astronomical unit of space, a number that may seem small but becomes staggering when multiplied across the volume of our galaxy. However, this estimate carries significant uncertainties. ATLAS has been systematically scanning our skies for 3 years and has detected only one interstellar object, but this could reflect detection biases rather than true scarcity. Smaller objects might pass unnoticed, or certain types of interstellar visitors might emit signals that current surveys fail to detect. The age-velocity relationship that places 3I-ATLAS in the thick disk population also provides insights into the galactic context of planetary system formation. If interstellar objects are representative of the planetesimals that formed around their parent stars, then the thick disk has been a prolific source of planetary building blocks for billions of years. This suggests that potentially habitable worlds may have been forming throughout most of our galaxy's history, not just in recent epochs when metallicity reached solar levels. 3I. ATLAS thus serves as more than an astronomical curiosity. It's a time machine that allows us to directly sample the conditions that prevailed when our galaxy was young. Its ancient composition provides ground truth for models of early planetary formation, while its successful billion-year journey demonstrates the viability of interstellar transport for life's building blocks across vast scales of space and time. 6. The Alien Hypothesis. Science meets speculation. 2,000 words. The discovery of any interstellar object inevitably invites comparison to 1I, Oumuamua, and the scientific firestorm it ignited. With 3I, ATLAS, this dynamic has repeated itself with even greater intensity, as the object's unusual characteristics have fueled a vigorous debate between mainstream scientific consensus and more speculative hypotheses. This controversy serves as a remarkable case study in scientific interpretation, public communication, and the process by which anomalies are investigated and ultimately resolved. Shortly after the confirmation of 3I, ATLAS's interstellar origin, Harvard astronomer Avi Loeb and his collaborators published a series of analyses proposing that the object's characteristics were so statistically unusual that an artificial origin deserved serious consideration. Unlike fringe conspiracy theories, this hypothesis emerged from peer-reviewed calculations and established astronomical methods, lending it a credibility that captured both scientific attention and public imagination. The case for an extraterrestrial artifact isn't based on a single smoking gun, but rather on what Loeb's team frames as a series of low-probability coincidences that, when viewed collectively, might suggest intelligent design rather than natural processes. This methodology, examining the joint probability of multiple independent anomalies, represents a legitimate, if controversial, approach to hypothesis testing in astronomy. The first and perhaps most compelling anomaly lies in the orbital geometry itself. The trajectory's near-ecliptic, retrograde alignment carries a calculated random probability of just 0.2%, a statistical improbability that immediately raises questions about whether this path represents chance or choice. For proponents of the artificial hypothesis, this alignment appears fine-tuned to enable an efficient reconnaissance survey of our solar system's inner planets, precisely the trajectory an intelligent probe might select for systematic observation. The second anomaly emerged from initial brightness estimates that suggested a nucleus diameter of approximately 20 kilometers. Based on theoretical models of interstellar object size distributions, rocky bodies of this scale should be extraordinarily rare in the galaxy. The probability of detecting such a massive visitor during humanity's brief period of astronomical awareness seemed to stretch the bounds of statistical credibility, leading some to question whether the object's apparent size might indicate artificial construction rather than natural formation. A third coincidence involves the object's precise targeting of planetary encounters. 3I-ATLAS's trajectory brings it within relatively close range of Venus, Mars, and Jupiter, a confluence of alignments with a calculated joint probability of less than 0.005%. From the perspective of the artificial hypothesis, these close approaches would provide an ideal opportunity for detailed reconnaissance of our solar system's most significant worlds, far beyond what random chance might reasonably deliver. The timing of the object's perihelion passage provides a fourth statistical curiosity. The fact that 3I-ATLAS's closest approach to the Sun occurs during a period when it's hidden from Earth's view by solar conjunction, an event with roughly 7% probability for any random trajectory, has been interpreted as potentially deliberate concealment. This orbital geometry would provide the perfect opportunity for what Loeb terms a reverse solar Oberth maneuver, where a spacecraft might fire its engines at the point of maximum velocity to break into a bound solar orbit, all while remaining invisible to Earth-based observers. The fifth anomaly initially appeared in the object's spectroscopic signature. Early observations revealed a dusty coma, but failed to detect the characteristic gas emissions, particularly cyanide, Cn, and diatomic carbon, C2, typically associated with active comets. For a supposedly natural comet displaying the brightness levels observed in 3I-ATLAS, this absence of gas emissions seemed inconsistent with established cometary physics, potentially indicating artificial construction or exotic composition. Beyond these statistical arguments, proponents of the artificial hypothesis point to more speculative considerations. The object's extreme velocity, 58 km per second, relative to the Sun, makes it practically impossible for humanity to intercept using current chemical rocket technology. This characteristic could represent a deliberate feature of a probe designed to conduct reconnaissance while remaining beyond our technological reach, ensuring that any intelligence gathering remains uncompromised. Some advocates have extended this reasoning into darker territory, suggesting that 3I-ATLAS might represent a possibly hostile probe operating under the principles of the dark forest hypothesis, a proposed solution to the Fermi paradox, suggesting that advanced civilizations remain silent to avoid detection by potentially predatory species. In this framework, 3I-ATLAS could represent reconnaissance by a civilization assessing human technological capabilities and potential threat levels. However, the overwhelming consensus within the astronomical community firmly rejects these extraordinary claims, not through dogmatic dismissal, but through systematic, evidence-based analysis that has methodically addressed each proposed anomaly. This scientific response demonstrates the robustness of peer review and the self-correcting nature of scientific inquiry when confronted with extraordinary hypotheses. The orbital anomaly, while statistically improbable, falls well within the realm of expected rare events given the vast number of planetary systems and ejected objects throughout our galaxy. Moreover, the near-ecliptic alignment might result from previously unknown dynamical effects in our galactic neighborhood or observational selection biases that favor the detection of objects moving near the plane of planetary orbits. Such biases could make ecliptic-aligned visitors appear more common than they actually are in the broader interstellar population. The size prevalence paradox has been definitively resolved through detailed photometric analysis. The confirmation of extensive cometary activity, a bright, dust-scattering coma surrounding a much smaller nucleus, means that 3I-ATLAS's observed brightness primarily reflects sunlight scattered by its dusty atmosphere rather than the surface area of its nucleus. Hubble Space Telescope observations constrain the actual nucleus to less than 5.6 kilometers in diameter, a size that's statistically far more plausible for natural formation and ejection from a distant planetary system. The apparent fine-tuning of planetary encounters dissolves under geometric analysis. Close approaches to inner solar system bodies are a direct and inevitable consequence of any trajectory that passes through the ecliptic plane. Rather than representing independent coincidences requiring separate explanation, these encounters are simply different manifestations of the same geometric relationship that produces the object's controversial orbital inclination. The perihelion concealment argument fails to account for the observational resources available during solar conjunction. While Earth-based telescopes will indeed lose sight of 3I-ATLAS during its closest solar approach, multiple spacecraft, including ESA's JUICE mission, NASA's Juno orbiter, and various Mars-based assets, will maintain clear lines of sight throughout this period. Any significant trajectory modification would be immediately detectable by these space-based observers, making the proposed stealth maneuver hypothesis readily testable and likely to be falsified. Most significantly, the absence of cometary gas emissions has been directly contradicted by subsequent observations. NASA's Neil Gehrels Swift Observatory definitively detected hydroxyl OH emission, the unmistakable signature of water vapor photodissociation, providing clear evidence of normal cometary outgassing. The initial absence of other volatile species like CN and C2 is entirely expected for a water-dominated comet at heliocentric distances greater than 3 AU, where these more exotic ices remain frozen and inactive. The scientific community's response exemplifies the application of Occam's razor, the principle that the simplest explanation, consistent with all available evidence, should be preferred over more complex alternatives. When 3I-ATLAS exhibits a fuzzy coma like a comet, displays spectral properties like a comet, shows measured rotation like a comet, and produces water vapor like a comet, the most parsimonious conclusion is that it is, indeed, a comet. This methodical dismantling of the artificial hypothesis doesn't diminish the value of asking extraordinary questions. Science advances through the investigation of anomalies, and the rigorous testing of alternative hypotheses strengthens our confidence in conventional explanations. The 3I-ATLAS controversy has spurred more detailed observations, refined theoretical models, and deeper consideration of selection effects in interstellar object surveys, all positive outcomes for astronomical research. Moreover, the debate highlights an important philosophical tension within scientific methodology. While mainstream astronomy applies conservative standards of evidence and favors natural explanations, some researchers advocate for more aggressive investigation of low-probability scenarios that might indicate technological signatures. This tension reflects broader questions about how science should approach the search for extraterrestrial intelligence and the investigation of potentially paradigm-shifting discoveries. The artificial hypothesis proponents argue that dismissing low-probability natural explanations in favor of technological alternatives represents a valid scientific approach, particularly when dealing with phenomena that might indicate intelligence. They contend that the burden of proof should not automatically favor natural over artificial explanations, especially when multiple statistical anomalies coincide in a single object. Critics respond that extraordinary claims require extraordinary evidence, and that the artificial hypothesis fails to meet established standards of scientific proof. They argue that eliminating improbable natural explanations doesn't automatically validate technological alternatives, and that the coincidence of multiple low-probability events, while unusual, remains far more likely than the existence of an extraterrestrial probe in our solar system. Ultimately, the 3I-ATLAS controversy serves as a powerful demonstration of science in action. Extraordinary claims have been subjected to rigorous scrutiny, alternative hypotheses have been tested against observational evidence, and the scientific community has reached consensus through the weight of accumulated data rather than authority or prejudice. The process has been messy, contentious, and sometimes acrimonious, exactly as it should be when investigating claims that could revolutionize our understanding of our place in the universe. 7. Media storm, public fascination, and the conspiracy ecosystem. 1. 200 words. The scientific debate surrounding 3I-ATLAS has been dramatically amplified by a media ecosystem hungry for sensational stories and a public fascinated by the possibility of extraterrestrial contact. The object's discovery coincided with an unprecedented democratization of astronomical observation and communication, creating a perfect storm of scientific inquiry, speculation, and conspiracy theorizing that has both advanced our understanding and complicated public communication about the discovery. Unlike previous interstellar visitors that were primarily studied by professional astronomers using major observatory facilities, 3I-ATLAS has become the subject of a remarkable grassroots observation campaign. The accessibility revolution in astronomy, driven by improved amateur telescopes, digital imaging technology, and global communication networks, has enabled skywatchers around the world to contribute meaningfully to the scientific characterization of this ancient visitor. The Astronomer Telegram, an online forum for rapid dissemination of astronomical discoveries and observations, has become mission control for this distributed research effort. Daily updates from amateur astronomers, small observatories, and citizen scientists provide a continuous stream of photometry, astrometry, and imaging data that supplements and sometimes surpasses observations from major facilities. This collaborative approach represents a fundamental shift in how astronomical discoveries are studied and understood. Miguel Alarcón and his international team of collaborators exemplify this new paradigm. Working with modest equipment but sophisticated analysis techniques, they've provided crucial refinements to measurements of 3I-ATLAS's tail structure, reporting extensions across more than 25,000 kilometers of space data that has been incorporated into professional publications and theoretical models. Their high-quality images, shared freely online, have captured public imagination while contributing genuine scientific value. This democratization of discovery has created a feedback loop between professional research and public engagement that would have been impossible during earlier interstellar visits. Real-time observations are shared instantly across social media platforms, analyzed by amateur astronomers with increasingly sophisticated software, and fed back into the scientific literature with unprecedented speed. The result is a level of public participation in cutting-edge astronomical research that blurs traditional boundaries between professional and amateur science. However, this accessibility comes with complications. The same platforms that enable valuable citizen science also facilitate the rapid spread of misinformation, speculation, and conspiracy theories. The artificial origin hypothesis, while originating from legitimate scientific analysis, has been transformed and amplified by social media into increasingly sensational claims that often bear little resemblance to the original scientific arguments. Headlines across mainstream media have consistently emphasized the AlienProbe narrative over the more nuanced but equally fascinating scientific discoveries about ancient galactic chemistry and planetary formation. Stories featuring phrases like mysterious interstellar visitor and possible alien technology generate more clicks and shares than detailed discussions of spectroscopic analysis or orbital mechanics, creating a distorted public perception of both the discovery's significance and the scientific consensus surrounding it. The viral nature of modern information spread has created what researchers term an infodemic around 3I-ATLAS, a proliferation of theories, interpretations, and claims that evolves faster than scientific analysis can address them. Social media algorithms, designed to maximize engagement, preferentially amplify controversial and emotionally resonant content over measured scientific analysis, further skewing public discourse toward sensational interpretations. Within this environment, the artificial origin hypothesis has spawned numerous derivative theories that extend far beyond the original scientific arguments. Some online communities have embraced more elaborate scenarios involving multiple alien civilizations, secret government knowledge, or connections to other unexplained phenomena. While these theories lack scientific support, they demonstrate the powerful human tendency to construct meaning and narrative around mysterious events. More concerning are the political conspiracy theories that have emerged around the timing of 3I-ATLAS's announcement. Some groups have suggested that the discovery was deliberately publicized to distract from terrestrial political events, or that government agencies are withholding crucial information about the object's true nature. These theories reflect broader patterns of institutional distrust and conspiratorial thinking that extend far beyond astronomical discoveries. Professional astronomers and science communicators face unprecedented challenges in this environment. Traditional approaches to science communication, emphasizing uncertainty, presenting multiple hypotheses, and acknowledging the limitations of current knowledge, often struggle against narratives that offer simple, dramatic explanations for complex phenomena. The careful hedging that characterizes good scientific practice can be misinterpreted as evasiveness or evidence of conspiracy. Yet the 3I-ATLAS story also demonstrates the potential for positive science communication in the digital age. Educational content creators have used the discovery as a springboard for explaining orbital mechanics, spectroscopy, and the scientific method to audiences that might never engage with these topics under normal circumstances. YouTube channels, Twitter threads, and TikTok videos have brought sophisticated astronomical concepts to millions of viewers, turning a single discovery into a massive informal education campaign. The JPL Horizons website has become an unexpected tool for public engagement, allowing anyone with internet access to track 3I-ATLAS's position and velocity in real time. This capability transforms passive consumers of science news into active participants in cosmic exploration, capable of witnessing the object's journey through our solar system with their own calculations and observations. Interactive online tools have enabled the public to visualize the object's trajectory, compare its properties to other interstellar visitors, and even plan their own observing sessions. This level of accessibility has created a generation of space enthusiasts who understand orbital mechanics not as abstract mathematical concepts, but as tools for tracking real objects moving through real space. The challenge for scientists and educators lies in channeling this enthusiasm toward accurate understanding while maintaining public interest in the genuine scientific discoveries that 3I-ATLAS represents. The object's true story as a messenger from the ancient galaxy carrying chemical fingerprints of planetary formation under radically different conditions is arguably more fascinating than AlienProbe scenarios, but requires more scientific background to fully appreciate. Successful science communication around 3I-ATLAS has emphasized the detective story aspects of the discovery, how astronomers use light curves to determine rotation periods, how spectroscopy reveals chemical composition, how orbital mechanics encode billion-year journeys across the galaxy. By presenting scientific analysis as a form of cosmic archaeology, educators have made technical concepts accessible while preserving their essential content. The controversy has also created valuable teaching moments about the scientific method itself. The systematic investigation of extraordinary claims, the role of peer review in validating hypotheses, and the self-correcting nature of scientific inquiry have all been illustrated through the real-time analysis of 3I-ATLAS. Students and the public have witnessed science in action, complete with its uncertainty, debate, and eventual convergence on evidence-based conclusions. Perhaps most importantly, the 3I-ATLAS phenomenon has demonstrated that public fascination with cosmic mysteries remains as powerful as ever. Whether driven by hopes of alien contact, fear of the unknown, or simple curiosity about our place in the universe, millions of people have engaged deeply with cutting-edge astronomical research in ways that would have been impossible just a generation ago. This engagement represents both an opportunity and a responsibility for the scientific community. The tools exist to make genuine scientific discovery accessible to unprecedented numbers of people, but only if researchers and educators can navigate the complex landscape of modern media and communication. The 3I-ATLAS story suggests that when science meets public curiosity in the digital age, the results can be both inspiring and challenging, much like the ancient comet that sparked the entire conversation. 8. The Great Test, Perihelion Passage and Verification, 1,500 words. As 3I-ATLAS continues its billion-year journey toward its 30th of October, 2025 perihelion passage, the astronomical community prepares for what may prove to be the most definitive test yet of extraordinary claims about interstellar visitors. The coming months represent a unique convergence of observational opportunity, technological capability, and scientific methodology that will either validate or definitively refute hypotheses about the object's artificial origin. The observation timeline for 3I-ATLAS has been carefully mapped to maximize scientific return while accommodating the geometric constraints imposed by its trajectory. Through September 2025, the comet remains ideally positioned for ground-based telescopic observations from Earth's night side. This window provides the final opportunity for detailed characterization using humanity's largest and most sophisticated Earth-based instruments before solar conjunction renders the object invisible to terrestrial observers. Major observatories worldwide have coordinated an unprecedented monitoring campaign during this crucial period. The James Webb Space Telescope, with observation time scheduled for August 2025, will conduct the most detailed spectroscopic analysis ever attempted of an interstellar object. JWST's powerful infrared instruments are uniquely capable of detecting trace volatile species, carbon monoxide, carbon dioxide, methane, ammonia, and exotic organic compounds that may be released as the comet's nucleus heats up during its final approach to the Sunday. These observations carry profound scientific implications beyond mere chemical inventory. The relative abundances of different volatile species encode information about the temperature and chemical conditions in the protoplanetary disk where 3I-ATLAS formed billions of years ago. Comparing these ratios to those found in solar system comets will provide direct evidence of how planetary formation processes varied between the ancient metal-poor thick disk environment and the more recent metal-rich thin disk conditions that created our own cosmic neighborhood. Ground-based facilities are contributing their own crucial pieces to the observational puzzle. The Hubble Space Telescope continues its high-resolution monitoring campaign, tracking changes in the comet's activity levels, coma structure, and nucleus properties as solar heating intensifies. The Neil Gehrels Swift Observatory maintains its ultraviolet surveillance, monitoring water production rates and searching for additional volatile species as they become active. Amateur astronomers worldwide have organized their own coordinated observation programs using the Astronomer Telegram and social media platforms to share real-time photometry, imaging, and positional measurements. This distributed network of observers provides nearly continuous monitoring capability that complements and extends the coverage possible with major facilities alone. Their contributions have already proven scientifically valuable and will become even more crucial during the critical perihelion period. As October approaches, 3I-ATLAS will disappear behind the Sun from Earth's perspective, beginning a period of solar conjunction that will last several weeks. For most astronomical purposes, this represents a frustrating observational gap during the most dynamically interesting phase of the comet's visit. However, for testing extraordinary claims about the object's nature, this period provides a unique and powerful opportunity for verification. Proponents of the artificial origin hypothesis have suggested that solar conjunction would provide the perfect cover for a clandestine reverse solar obirth maneuver, a spacecraft braking burn executed at the point of maximum velocity to enter a bound orbit around the Sunday. Such a maneuver would be invisible to Earth-based observers, but would produce easily detectable changes in the object's trajectory that would become apparent when it re-emerges from behind the Sun in December. This hypothesis represents a rare example of a genuinely testable prediction in the extraterrestrial intelligence debate. Unlike many claims about alien visitation, which rely on absence of evidence or unfalsifiable assertions, the proposed solar conjunction maneuver makes specific, quantitative predictions about observable phenomena that can be definitively confirmed or refuted through standard astronomical measurements. The key to this test lies in the network of spacecraft distributed throughout the inner solar system that will maintain clear sightlines to 3I-ATLAS throughout its solar passage. ESA's Jupiter Icy Moons Explorer, JUICE, currently en route to the Jovian system, will be positioned to observe the comet continuously during its closest approach to the Sunday. NASA's Juno spacecraft, orbiting Jupiter, provides another independent viewing platform with high-precision navigation and tracking capabilities. Closer to the Sun, various assets at Mars, including orbiting spacecraft and potentially surface-based instruments, will have unobstructed views of 3I-ATLAS during the critical perihelion period. These robotic observers can precisely track the comet's position and velocity, providing the astrometric data necessary to detect any deviation from its predicted natural trajectory. The predicted natural trajectory itself has been calculated with extraordinary precision using the extensive observational data collected since the comet's discovery. Multiple independent research groups have refined orbital solutions that account for gravitational perturbations from all major solar system bodies, as well as non-gravitational forces from cometary outgassing. These models make specific predictions about where 3I-ATLAS should be located and how it should be moving when it re-emerges from solar conjunction. Any significant deviation from these predictions, particularly the kind of velocity change that would result from a substantial propulsive maneuver, would be immediately apparent in post-conjunction observations. The required change in velocity to enter a bound solar orbit from 3I-ATLAS's current trajectory is substantial, on the order of tens of kilometers per second, making it easily detectable with current measurement capabilities. When 3I-ATLAS re-emerges from behind the Sun in early December 2025, it will face a battery of Earth-based telescopes ready to precisely measure its position and trajectory. The comparison between predicted and observed orbital parameters will provide a definitive test of whether any artificial intervention occurred during the solar passage. This represents a unique opportunity in the search for extraterrestrial intelligence, a hypothesis that makes specific, falsifiable predictions about observable phenomena. The December observations will also provide a second window for detailed spectroscopic analysis, as the comet's nucleus will have been subjected to intense solar heating during perihelion passage. This thermal processing may release volatile species that remained frozen during the object's initial approach, providing new insights into its chemical composition and internal structure. Changes in activity levels, coma composition, and outgassing patterns will all be carefully documented and compared to models of natural cometary evolution. Beyond the immediate scientific and hypothesis testing value, the 3I-ATLAS perihelion passage represents a remarkable demonstration of modern astronomy's capabilities. The coordination of space-based and ground-based assets, the integration of professional and amateur observations, and the real-time analysis and dissemination of results showcase a field that has evolved far beyond the individual observer with a single telescope. The public engagement aspect of these observations cannot be overlooked. Tools like JPL Horizons allow anyone with internet access to track 3I-ATLAS's journey in real time, calculating its position and velocity throughout the solar conjunction period. This accessibility transforms the perihelion passage from an abstract astronomical event into a participatory experience where millions of people can follow along with cutting-edge scientific research. Educational institutions worldwide have incorporated 3I-ATLAS tracking into their curricula, using the comet's journey to teach orbital mechanics, spectroscopy, and the scientific method. Students are not just learning about these concepts, but applying them to analyze data from an active astronomical discovery, creating unprecedented opportunities for hands-on science education. The perihelion passage also serves as a powerful demonstration of the falsifiability principle that lies at the heart of scientific methodology. Regardless of one's initial beliefs about 3I-ATLAS's nature, the upcoming observations will provide objective, measurable data that can confirm or refute specific hypotheses. This process exemplifies how science advances through the testing of competing explanations against empirical evidence. As the 30th of October 2025 approaches, the astronomical community prepares for what may prove to be one of the most closely watched perihelion passages in history. Whether 3I-ATLAS emerges in December as a natural comet following its predicted trajectory or reveals evidence of artificial intervention, the observations will mark a defining moment in our understanding of interstellar visitors and our methods for studying them. The ancient wanderer from the galactic dawn continues to teach us not just about the early history of planetary formation, but about the nature of scientific inquiry itself. 9. Looking ahead, the Rubin Revolution. 1. 500 words. The study of 3I-ATLAS represents far more than the characterization of a single remarkable object. It marks the final chapter of one era in interstellar object research and the opening of another. As this ancient comet completes its journey through our solar system and returns to the cosmic void, astronomers are preparing for a revolution in our ability to detect and study visitors from distant stars, one that will transform the field from the analysis of individual anomalies into a comprehensive statistical science. At the heart of this transformation lies the Vera C. Rubin Observatory, whose pre-discovery imaging of 3I-ATLAS provided a tantalizing preview of capabilities that will soon reshape our understanding of the galaxy's planetesimal population. The Rubin Observatory, also known as the Legacy Survey of Space and Time, LSST, represents the culmination of decades of technological advancement in wide-field astronomical surveying, combining unprecedented sensitivity with systematic coverage of the entire visible sky. Currently, interstellar object discovery proceeds at a frustratingly slow pace. The detection of 3 confirmed visitors, Oumuamua, Borisov, and 3I-ATLAS, over 8 years, provides tantalizing glimpses of a vast population while leaving fundamental questions unanswered. Are these objects representative of typical interstellar planetesimals, or do they represent statistical outliers that happen to pass close enough to our solar system for detection. What is the true size distribution of objects wandering between the stars? How do chemical compositions vary between planetesimals formed around different types of stars and in different galactic environments? The Rubin Observatory will answer these questions through sheer statistical weight. Projections based on its technical capabilities and the limited population estimates derived from current discoveries suggest that Rubin will detect dozens, perhaps hundreds, of interstellar objects during its initial decade of operations. This represents an increase in discovery rate of more than an order of magnitude, sufficient to transform interstellar object studies from curiosity-driven case studies into rigorous population analysis. The observatory's revolutionary capability stems from its unique combination of a massive 8.4-meter primary mirror, a 3.2 gigapixel camera, and an observing strategy that images the entire visible sky every few nights. This systematic approach ensures that no region of sky remains unmonitored for extended periods, dramatically increasing the probability of detecting fast-moving interstellar visitors during their relatively brief passages through the inner solar system. Equally important is Rubin's sensitivity to faint objects. While current surveys can detect interstellar visitors only when they approach within a few astronomical units of the Sun and become bright enough for observation, Rubin will be capable of spotting objects at much greater distances. This extended detection range provides several crucial advantages for scientific characterization. First, earlier detection means longer observation windows. Instead of discovering objects after they've already passed perihelion and are racing back toward interstellar space, as happened with Oumuamua, Rubin will typically find visitors while they're still far from the Sun, providing months or even years for detailed study. This extended timeline enables comprehensive spectroscopic analysis, precise orbit determination, and coordinated observations across multiple wavelengths and instruments. Second, the ability to detect objects at larger heliocentric distances reduces selection biases that currently skew our understanding of the interstellar population. Present surveys are most sensitive to objects that become highly active as they approach the Sun, potentially missing a large population of less volatile or inactive bodies. Rubin's superior sensitivity will detect objects based primarily on their size and reflectivity, rather than their activity levels, providing a more representative sample of the true interstellar population. The transition from individual case studies to population statistics will enable astronomers to address fundamental questions about planetary system formation and evolution throughout the galaxy. By analyzing the size distribution of detected objects, researchers can test theoretical models of how planetesimals form and are ejected from their birth systems. Chemical composition studies of large samples will reveal how metallicity, stellar mass, and other factors influence the materials available for planet formation in different galactic environments. Perhaps most intriguingly, population studies may reveal patterns in the origins and trajectories of interstellar visitors. While 3I-ATLAS appears to originate from the galaxy's thick disk population, future discoveries may show clustering around particular stellar moving groups, evidence for preferential ejection from certain types of planetary systems, or correlations between chemical composition and galactic origin. Such patterns would provide unprecedented insights into the history and structure of planetary formation throughout the Milky Way. The Rubin revolution extends beyond mere discovery to encompass rapid response characterization capabilities. The observatory's real-time data processing and alert systems will automatically identify potential interstellar visitors and distribute alerts to the global astronomical community within minutes of detection. This rapid notification will trigger coordinated follow-up observations from specialized facilities around the world, ensuring that maximum scientific value is extracted from each discovery. Advanced planning for this future is already underway. ESA's Comet Interceptor mission, scheduled for launch in 2029, exemplifies the forward-thinking approach required to capitalize on the coming discovery boom. Rather than targeting a predetermined object, Comet Interceptor will be placed in a parking orbit at the Sun, Earth Lagrange Point 2, where it will await the discovery of a suitable target, either a pristine, long-period comet from our own Oort cloud, or, in the most scientifically exciting scenario, a newly discovered interstellar visitor. The spacecraft carries a suite of instruments designed for the rapid, comprehensive characterization of previously unstudied objects. When a suitable target is identified on an interceptable trajectory, the mission can be quickly retargeted and dispatched for humanity's first close-up examination of a truly ancient, unprocessed remnant of planetary formation. The scientific return from such an encounter would dwarf anything possible through remote observation, providing direct measurements of surface composition, internal structure, and physical properties impossible to obtain from Earth-based telescopes. Current technological limitations make intercepts of objects like 3I-ATLAS impossible. Its 58 km per second velocity exceeds the capabilities of chemical propulsion systems by a wide margin. However, future discoveries may include slower-moving objects on more accessible trajectories, particularly visitors from nearby stellar systems or objects perturbed into unusual orbits by close encounters with solar system planets. Creative mission concepts are already being developed to maximize intercept opportunities. Multi-spacecraft missions could deploy multiple probes to intercept different objects, or to observe single objects from multiple vantage points. Solar sail technology might enable intercepts of high-velocity targets by using solar radiation pressure for propulsion over extended periods. Ion drives and other advanced propulsion systems could extend the range of accessible objects beyond what's currently possible with conventional rockets. The scientific justification for such ambitious missions becomes stronger with each new interstellar discovery. 3I-ATLAS has demonstrated that these objects carry irreplaceable information about the conditions prevailing during planetary formation in different stellar environments and galactic epochs. Direct sampling through spacecraft encounters would provide chemical and isotopic analyses impossible to achieve through spectroscopy alone, opening entirely new avenues of research into the early history of planetary systems. International cooperation will be essential for maximizing the scientific return from the coming discovery boom. No single nation or organization possesses all the resources necessary for comprehensive interstellar object characterization. The success of the 3I-ATLAS observational campaign, which seamlessly integrated data from space-based and ground-based facilities operated by multiple countries and organizations, provides a model for future collaborative efforts. Data sharing agreements, coordinated observation protocols, and rapid communication systems will need to be established and tested before the Rubin Observatory begins full operations. The astronomical community must be prepared to respond quickly and efficiently to potentially dozens of interstellar discoveries each year, ensuring that observational resources are allocated optimally and that scientific opportunities are not missed due to coordination failures. The educational and public engagement opportunities presented by this new era are equally exciting. Instead of waiting years between interstellar visits, students and amateur astronomers will have regular opportunities to participate in cutting-edge research. Real-time tracking of newly discovered objects, spectroscopic analysis projects, and citizen science initiatives could transform astronomy education by providing direct experience with active scientific discovery. As 3I-ATLAS prepares to depart our solar system, it leaves behind more than just scientific data and spectacular images. It has provided a preview of a future where interstellar visitors are not rare curiosities, but regular subjects of systematic study. The ancient comet's journey through our astronomical consciousness marks both an ending and a beginning, the culmination of humanity's first tentative encounters with messengers from distant stars, and the opening of an era where such encounters will illuminate the full scope of planetary formation throughout our galaxy's history. The passage of 3I-ATLAS through our solar system will be remembered not merely as the visit of another cosmic wanderer, but as a transformative moment in our understanding of planetary formation, scientific methodology, and our place within the galactic community. This ancient messenger, from the thick disk of the Milky Way, has delivered lessons that extend far beyond its impressive size, unusual trajectory, or controversial hypotheses about its origin. Perhaps the most profound scientific legacy of 3I-ATLAS lies in its demonstration that large, water-rich planetesimals could form efficiently in the metal-poor environment of the ancient galaxy. For decades, theoretical models had suggested that planetary formation might be severely hampered in low metallicity environments, where the scarcity of heavy elements would limit the raw materials available for building solid bodies. The existence of 3I-ATLAS, a substantial, actively outgassing comet that formed billions of years before our solar system, challenges these assumptions and fundamentally revises our understanding of when and where planetary building blocks could assemble throughout cosmic history. The implications extend directly to astrobiology and the search for life in the universe. If large water-bearing planetesimals were common in the ancient galaxy, then the chemical prerequisites for life water, organic compounds, and complex chemistry were being distributed throughout stellar systems far earlier than previously thought. This pushes back the potential timeline for life's emergence in the galaxy by billions of years, suggesting that habitable worlds may have existed when the universe was less than half its current age. The comet's pristine chemical composition provides an unparalleled window into the conditions that prevailed during planetary formation in a fundamentally different galactic environment. Its spectral signature, dominated by water, ice, and primitive, organic-rich material similar to the most chemically primitive meteorites in our own solar system, suggests remarkable consistency in the basic processes of planetesimal formation across vast differences in stellar metallicity and galactic epoch. This consistency implies that the fundamental physics of planet formation is more robust and universal than many theoretical models had predicted. 3I-ATLAS has also served as a powerful demonstration of how modern astronomy has evolved into a truly global, collaborative enterprise. The object's discovery and characterization involved dozens of observatories across multiple continents, space-based assets operating throughout the inner solar system, and contributions from amateur astronomers whose sophisticated equipment and analysis techniques rival those of professional facilities just decades ago. This distributed, interconnected approach to cosmic discovery represents a new paradigm in scientific research, one where major discoveries emerge not from isolated observations, but from the coordinated efforts of a worldwide community. The controversy surrounding the object's potential artificial origin has provided valuable insights into the process of scientific inquiry itself. The systematic investigation of extraordinary claims, the application of statistical analysis to unusual phenomena, and the ultimate resolution of anomalies through additional observations demonstrate the self-correcting nature of scientific methodology. More importantly, the debate has shown how science can address even the most speculative hypotheses through testable predictions and objective measurements. The artificial origin hypothesis, while ultimately unsupported by evidence, served a constructive purpose in the scientific process. It forced astronomers to examine their assumptions, refine their theoretical models, and develop more sophisticated statistical frameworks for evaluating unusual observations. The rigorous testing of this hypothesis has strengthened confidence in conventional explanations while establishing methodological precedents for evaluating future claims about potential technological signatures in astronomical data. 3I-ATLAS has revolutionized public engagement with cutting-edge astronomical research. The democratization of observation capabilities, combined with real-time data sharing and social media platforms, has enabled millions of people to participate directly in the scientific process. Amateur astronomers have contributed genuinely valuable data. Students have analyzed real observations for their coursework, and the general public has followed along with active research in ways that would have been impossible during previous interstellar visits. This engagement has revealed both the opportunities and challenges of science communication in the digital age. While social media platforms have enabled unprecedented access to scientific discovery, they have also facilitated the rapid spread of misinformation and speculation. The 3I-ATLAS story demonstrates the need for scientists to develop new strategies for communicating complex, uncertain, and evolving research to audiences accustomed to simple, definitive answers. The object's legacy extends to the future of interstellar object research. As the last major discovery of the current generation of sky surveys, 3I-ATLAS provides crucial baseline data for planning the next phase of cosmic archaeology. Its detection and characterization have informed the design of future observation campaigns, established protocols for rapid response spectroscopy, and demonstrated the importance of extended observation windows for comprehensive analysis. The lessons learned from studying 3I-ATLAS will directly benefit the interpretation of future discoveries by the Vera C. Rubin Observatory and other next-generation facilities. The techniques developed for analyzing its unusual orbital characteristics, the methods established for separating nucleus properties from coma contamination, and the collaborative frameworks created for coordinating global observation campaigns provide a foundation for studying the dozens or hundreds of interstellar visitors that lie ahead. Perhaps most significantly, 3I-ATLAS has established interstellar object research as a legitimate and important subdiscipline of astronomy. What began as a series of serendipitous discoveries has evolved into systematic science with dedicated observational resources, theoretical frameworks, and long-term research programs. The field has moved beyond simply cataloguing unusual visitors to addressing fundamental questions about the demographics, origins, and physical properties of planetesimals throughout the galaxy. The comet has also demonstrated the value of maintaining an open mind while applying rigorous scientific standards. The investigation of its unusual characteristics, from statistical orbital anomalies to unexpected spectral properties, required astronomers to consider multiple hypotheses simultaneously while allowing the weight of evidence to guide their conclusions. This balanced approach, neither dismissing anomalies too quickly nor accepting extraordinary explanations without sufficient proof, exemplifies the best practices of scientific inquiry. On a more philosophical level, 3I-ATLAS serves as a humbling reminder of our cosmic context. This ancient wanderer had been journeying through the galaxy for billions of years before Earth existed, carrying with it the chemical fingerprints of stellar systems we will never see and planetary formation processes we can only study through such rare messengers. Its visit connects us directly to the deep history of our galaxy and the cosmic processes that have shaped the distribution of matter, energy, and potentially life throughout the Milky Way. The object's extreme age, potentially 7 to 11 billion years, places it among the most ancient intact objects ever studied by human science. While we can observe distant galaxies as they existed billions of years ago through the light travel time effect, 3I-ATLAS provides something far rarer: a physical sample of ancient cosmic chemistry that we can analyze in detail with our most sophisticated instruments. It represents a form of time travel, bringing the early galaxy directly to our laboratories for examination. As 3I-ATLAS completes its passage through our solar system and returns to the interstellar void, it leaves behind a transformed scientific landscape. The techniques developed for its study, the international collaborations forged during its characterization, and the theoretical insights gleaned from its properties will continue to influence astronomical research for years to come. Future interstellar visitors will be studied using methods pioneered during this ancient comet's brief residency in our cosmic neighborhood. The story of 3I-ATLAS ultimately demonstrates that the most profound scientific discoveries often emerge not from finding what we expect, but from carefully studying what surprises us. This billion-year-old messenger from the galactic dawn has taught us as much about the practice of science as about the ancient cosmos it represents, showing that wonder and rigor, speculation and skepticism can coexist productively in the endless human quest to understand our place in the universe. Conclusion: The Eternal Journey, 800 words. As the autumn of 2025 draws to a close and 3I-ATLAS fades into the cosmic distance, we find ourselves forever changed by this brief encounter with deep time. This ancient wanderer, older than our solar system itself, has completed its reconnaissance of our small corner of the galaxy and begun the long journey back to the stars, carrying with it the faint signatures of Earth's radio emissions, and perhaps the last glimpse it will ever have of our particular civilization. The story of 3I-ATLAS is ultimately a story about time, about the vast scales on which the universe operates, and the fleeting nature of our observations within cosmic history. For billions of years, this pristine relic of the galaxy's youth traveled through the emptiness between stars, a silent witness to the evolution of the Milky Way, from its metal-poor adolescence to the chemically enriched spiral we inhabit today. Its nucleus preserves conditions and processes that vanished from our galactic neighborhood before the sun was born, making it perhaps the oldest intact object humans have ever studied in detail. Yet, for all its antiquity, 3I-ATLAS has proven to be thoroughly modern in its impact on astronomical science. Its discovery marked the maturation of automated sky surveys into a truly global early warning system for cosmic visitors. Its characterization demonstrated the power of international collaboration and citizen science in the digital age. Its controversial hypotheses illustrated the robust self-correcting mechanisms of scientific inquiry, and its impending departure signals the transition from the era of serendipitous discovery to the age of systematic cosmic archaeology that awaits us with next-generation facilities. The scientific legacy of this interstellar messenger extends far beyond its individual measurements and properties. It has established that water-rich planetesimals could form efficiently in the ancient metal-poor galaxy, pushing back the potential timeline for habitable world formation by billions of years. It has demonstrated that the fundamental processes of planetary system evolution operate consistently across vast differences in stellar chemistry and galactic environment. And it has provided the first direct evidence that substantial planetesimals are regularly ejected from distant systems and wander the galaxy as cosmic nomads, carrying chemical information across space and time. Perhaps most importantly, 3I-ATLAS has shown us that we live in a galaxy teeming with wanderers. The detection of 3 interstellar objects in just 8 years suggests a vast population of ejected planetesimals, failed planets, and ancient comets drifting through the spaces between stars. Each carries its own story of formation, evolution, and ejection, waiting for the moment when its path might intersect our growing sphere of observational capability. The coming decades will bring us into regular contact with these messengers from distant worlds. The Vera C. Rubin Observatory and its successors will transform interstellar visitor encounters from rare, celebrated events into routine scientific observations. We will build statistical samples large enough to answer fundamental questions about planetary formation throughout the galaxy. We will trace chemical evolution across cosmic time through direct analysis of objects that formed under conditions no longer present in our local galactic environment. Some future visitor may prove accessible to spacecraft intercept, allowing us to collect physical samples and conduct detailed in situ analysis of materials that formed around distant stars. Others may carry more exotic compositions or unusual properties that challenge our understanding of planetary formation processes. A few might even exhibit characteristics so anomalous that they revive serious consideration of artificial origins, though 3I-ATLAS has shown us how rigorously such claims must be tested against the weight of evidence. But the most profound impact of 3I-ATLAS may be philosophical rather than scientific. This ancient comet has connected us viscerally to the deep history of our galaxy and our place within a community of worlds that extends across space and time. It has shown us that planetary formation is not a local phenomenon confined to our solar system or even our stellar neighborhood, but a galactic process that has been operating throughout cosmic history. We are not alone in our corner of the galaxy, not because 3I-ATLAS carried signals of intelligent life, but because it demonstrated that the building blocks of planetary systems and potentially life itself have been forming and dispersing throughout the Milky Way for most of its existence. The water now flowing in Earth's oceans, the organic compounds that form the basis of terrestrial biology, and the rocky materials that comprise our planet were all being assembled into planetesimals around distant stars when our galaxy was young. As 3I-ATLAS disappears into the constellation Draco and begins its return journey to interstellar space, it carries with it our first deliberate message to the cosmos beyond our solar system. Radio signals from Earth, traveling at the speed of light, will eventually overtake the ancient comet and continue outward into the galaxy, marking this moment when a 4-6 billion-year-old civilization briefly encountered an 1 billion-year-old wanderer from the galactic dawn. In the end, 3I-ATLAS has reminded us that we are all travelers in space and time, temporary arrangements of stellar material on a small planet orbiting an unremarkable star in an ordinary galaxy. But it has also shown us that even temporary arrangements can achieve extraordinary things. We can build instruments to detect ancient visitors, develop theories to explain their properties, and create collaborative networks to study them together. We can ask questions about cosmic history and find answers written in the orbital mechanics and chemical composition of wandering worlds. The ancient messenger has departed, but its legacy endures in our transformed understanding of planetary formation, our improved methods for studying cosmic visitors, and our deeper appreciation for the timescales on which the universe operates. 3I-ATLAS came to us from the galactic dawn, and in studying it, we have glimpsed both our cosmic past and our astronomical future. The eternal journey continues, and we are now better equipped to understand the messages it carries.